Okay, so now on to infinite collapsing ordinals. So this is basically a way where we can get far, far, far beyond anything we've done so far, and we can do it within a single function. So don't worry about this too much. This is kind of just for me, just to remember where I am and everything. So first thing we're going to start with is we're learning an entirely different thing here. So we're going to start at the very beginning. I want you to imagine a set S, and this is going to contain 0, 1, omega, and this time something new, capital Omega. Now I want you to imagine this is kind of like our toolbox. This is what we're going to use to construct the ordinals. And basically what we're allowed to do with our toolbox is we can take anything from inside this and we can use addition, multiplication, and an exponentiation, basically. So we're going to define our first set, C0, so C of 0. And this is going to be exactly what I just said. This is going to be anything that we can do in here with addition, multiplication, and exponentiation. So we're going to have this is equal to things like 0, you can do 1, you can do 2, omega, omega plus 1, omega times 2. We can have omega to the omega, omega to the omega to the omega, blah, 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 etc., etc. And we can even have things to do with this one here. So we can have this plus 1, capital omega plus 1, capital omega to the capital omega. But we're not going to worry too much about this here because this ordinal is going to come in later. For now, we're just going to kind of deal with these ones here. So there's a whole bunch of things that we can do with, and these are just a few of them. So these are a few things that C of 0 contains. Now, what's the first ordinal that cannot be reached in this way? Well, it's going to be an infinite tower of omegas, right? Because we're only allowed to do a finite addition, multiplication, exponentiation, whatever. So an infinite tower of omegas will be the first infinite ordinal that is not accessible in this set. So we're going to give that a name. We're going to call that psi of 0. Remember, this is psi, not phi, like we had in the previous ones, Veblen notation. So this is different. This is psi. And this is our collapsing function, basically. So we're going to call psi of 0, our first function, is going to be the first infinite ordinal unreachable from C0, which is going to be an infinite tower of omegas, which, as we know, is epsilon naught. Okay, so now moving on, we're going to go to C of 1. Now C of 1 is our previous set, so C of 0, and I'm going to use the union symbol there. So this just means this in addition to that. So this combined with any operations of this using addition, multiplication, and exponentiation, basically. So we can have anything that we had in here, plus we can have things like, epsilon naught. We can have epsilon naught plus 1, epsilon naught times omega, epsilon naught to the epsilon naught, epsilon naught to the epsilon naught to the epsilon naught. And we're going to label the first infinite ordinal not accessible from this one as psi of 1. And this is going to be an infinite tower of epsilon naughts, which is equal to epsilon 1. Now before I go any further, because this is something that tripped me up, how does this equal epsilon 1? Because I taught you that an infinite tower of omegas with epsilon naught plus 1 is equal to epsilon 1. Well, the answer is they're both equal to epsilon 1. And before I go any further, I'm going to show you why. So it's important to write some of this down, or if you want to kind of reference this, so I'll ask you to write this down. Wonderful thing about video is I don't have to wait for you guys to write it down because you could just press pause. Good stuff. Okay. So a small aside, showing that things like an infinite tower of omegas, blah, 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 with epsilon naught plus 1 at the top, is the same as an infinite tower of epsilon naughts. So why is this? Okay, well, let's take a small example. Let's take, if I were to have epsilon 1 diagonalized to 3, if I were to have something like omega to the omega to the omega to epsilon naught plus 1. Well, let's evaluate this. Epsilon naught plus 1, we can use rules of exponentiation or whatever. We can take omega to the epsilon naught times omega. And then, okay, so let's do that. I'll try not to do too many steps in my head here. I'll try to write this out. Times omega. Well, now we have an omega to epsilon naught all by itself, which, as we know, because epsilon naught satisfies the equation omega to the a equals a, this just collapses into omega naught. So let's just get rid of that. This just turns into epsilon naught. So now we have an omega to the epsilon naught times omega. We can use another rule of exponentiation with this part here, and we can turn this into omega to the epsilon naught to the power of omega. So that's another property of exponents or whatever. If you have this times omega, this is the same as putting this in brackets, this to the epsilon naught, all to the power of omega. That's another thing we can do. And once again, we have an omega to the epsilon naught all by itself. This collapses into just epsilon naught, so we get omega to the epsilon naught to the omega. So what do we do now? Well, we're going to use a property of infinite ordinals that's a little bit useful. If you remember, 1 plus omega is still equal to omega, right? So I can sneak a 1 in the beginning of here, so I get omega to the epsilon naught. 1 plus omega. I'm allowed to do that because this is still equal to omega. And I can do that little trick because it'll help me with this rearrangement type of thing or whatever. So now we're going to use rule of exponents again. So we're going to have omega to the epsilon naught to the power of 1 is just epsilon naught. And we're going to go times epsilon naught to the omega, because you see what I'm doing here, I'm using rules of exponents, so I take this one here to the power of here and multiply it here. Alright, so now I'm going to use this same rule that I used here, or whatever, so I have omega to the epsilon naught on the inside, and I have epsilon naught to the omega as the exponent. This collapses to epsilon naught, and I just get epsilon naught to the epsilon naught to the omega. And now the thing here is, if I were to have the original one here as 4 omegas with an epsilon naught plus 1 at the top, if I were to do this same trick with a little bit of extra stuff, whatever, like adding 1 in the beginning, whatever, it's a little bit more complicated, but you can do the same thing no matter how many omegas you have in here. I would end up with epsilon naught to the epsilon naught to the epsilon naught of omega. So for every omega that I have here, every tower of omegas, I have that many minus 1 epsilon naughts in a tower here. So if this is infinite, this is the same as saying this is an infinite tower of epsilon naughts at the top. And we can kind of disregard this omega here, because you can imagine, like, if we diagonalize this, this thing doesn't cause this whole thing to expand. It just turns into like a 3 or whatever, and then it's gone or whatever. So it's not the same as adding 1 that causes this huge expansion of the function. It's just a little omega up here. It's just going to diagonalize and then disappear. So for all intents and purposes, if we have an infinite tower, this is the same as saying an infinite tower of epsilon naughts. And another interesting property is we can do this, we can use this for other things. And you're going to see me use this, so I'll show you so you don't get confused, whatever. If we have an infinite ordinal that's bigger, that's equal to or bigger than zeta naught, we can write down its infinite tower. So let's say I had like zeta 1 or something, of zeta 1, an infinite tower of zeta 1s. I could also write that as epsilon zeta 1 plus 1. And the reason for this is exactly the same as the arithmetic I did before. So basically, I write this down in our usual form, so omega to the omega to the omega to the omega, blah, 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 with epsilon zeta naught, and then this plus 1. So remember that this down here, this is zeta 1 plus 1 in the subscript. This here is epsilon zeta naught, and this whole thing is plus 1, so it's a little bit different. The reason why it has to be as big or bigger than zeta naught is so that this function here collapses. Because then we just get the zeta function. Okay, I'm sorry, this is not, this is still zeta 1. That's not zeta naught. Okay, yeah, so this function collapses and I just get zeta 1 plus 1, and I do my little arithmetic trick. I rearrange things and I end up just getting an infinite tower of this function here, whatever. So this infinite tower, another way of writing it is epsilon sub zeta 1 plus 1. And you can replace this with any function that's as big or bigger than zeta naught. So you're going to see me use that sometimes, so I don't want you to get confused. That one kind of threw me for a loop in the beginning, and I had to kind of figure it out, so I wanted to show you that. Okay, so now where were we? All right, okay. So yeah, I'll write down what I had before just so we can kind of have like a thing. So we had a C of 0 was everything that we can, I'll write down S2, so I'll write S up here. S is that toolbox that we used of 0, 1, omega, and capital omega. C1 was a bunch of things that we could have, like all operations of this, basically addition, multiplication, and an exponentiation. Omega to the omega, blah, 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 blah. The first collapsing function was the smallest ordinal that wasn't accessible from this, which was an infinite tower of omegas, which is the same as epsilon naught. C1 is everything in here, so everything in our first function, plus, or union, addition, multiplication, or an exponentiation of this function here. So epsilon naught plus 1, epsilon naught, blah, 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 etc., etc., etc. And then we call psi of 1 the first ordinal that's inaccessible from this, and that's an infinite tower of epsilon naughts, which you know now is equal to epsilon 1. So this trend kind of continues on, and we can say that generally psi of A is going to equal epsilon of A. So this is kind of like an epsilon building function type of thing. But we don't want to take this too literally, because once we get past a certain point, whatever, this does not work. And the point where this does not work anymore is when psi is equal to zeta naught. And as it turns out, this just turns into zeta naught, and the function is stuck. The reason why this function gets stuck is we have to go back to the original definition of this collapsing function. We're building sets and then finding out what the smallest ordinal that does not exist in this set. So we're building this set bit by bit, bit by bit. So if you can imagine, the easiest way to think about this is anything that this set can build, you can plug it back into the function to get something bigger or whatever. So if I had this collapsing function, I'll start with let's say of 3. That's going to equal epsilon 3. Well, anything that this function can build, I can plug it back into the function or whatever. So let's say I had epsilon 3. That would equal epsilon sub epsilon of 3. And remember, I mean, to get to this, I mean, you'd have to go through a lot of different sets, finding smallest ordinals all the way through to get to this. But eventually you would get to it. It is possible to get this function if you go through enough of the sets or whatever. So basically, anything you can make with the function, you can plug back in. But what's the limit of this? Well, the thing is, you can never get an infinite nesting of epsilons. You can only get finite nestings of epsilon. So in order to get to zeta naught, you'd have to be able to build an infinite nestings of epsilon to plug into the function in the first place. And you can never get that with our original set S, whatever. You can't get there through a finite process. So this function gets stuck at zeta naught. So because we can never plug anything bigger into the function or whatever, stuff like the psi of zeta naught plus 1 is also zeta naught. It doesn't get any bigger. We can plug anything we want in here. It doesn't get any bigger. So this is kind of silly. I mean, we have this infinite collapsing function that's supposed to get us huge, huge ordinals, and already we're stuck at a lowly zeta naught, which we reached like 3 videos ago. So what do we do from here? So this is where our friend, capital omega, comes in. So I'm going to define that, basically. It's going to seem a little bit strange, but we're going to define this as a very, very big ordinal. It doesn't even have to be a definitive ordinal. We're just going to define it as something way bigger than anything we're ever going to need. So it's going to be bigger than anything we're going to create with infinite collapsing ordinals themselves or whatever. So it's a really, really, really big infinite ordinal. And the reason why we're allowed to do that is because the function gets stuck. It's actually very, very important that the function gets stuck, because then we can do something like this. we can do psi of capital omega. Well, we know that anything bigger than zeta naught is just going to be zeta naught because the function's stuck. So it doesn't matter how big and indeterminate this ordinal is. It's going to turn into something that we know. And this is why this thing is called collapsing functions, because it takes something really, really big and it collapses to something that we know. Okay, so we know that this is a really, really big function, but this is still just going to be zeta naught. So where do we go from here? Well, now we can do something a little bit tricky, because capital omega is in our original set S, and in our original set S, we're allowed to do things like addition, multiplication, and exponentiation. So we're allowed to do things like psi of omega plus 1. And we can do this because it's in our original set. We artificially put it in there or whatever so that we can continue on and do operations or whatever. So this is going to continue the trend now. So now we're going to have, this is going to be epsilon zeta naught plus 1, or the smallest ordinal, the smallest epsilon ordinal after zeta naught. And then we can continue on. We can do psi of capital omega plus 2 is going to equal epsilon sub zeta naught plus 2, blah, 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 blah. And this is going to keep on going, but this function is going to get stuck again.